Result for that sulfate at the start. I'm going to leave lone pairs off just to go quicker. Single bondeds would have 3 lone pairs. The double bonded would have 2. Well, basically you swap a double bond and a charge. And so there's an option where I could swap these two. I'd have a sulfur, double bond up, double bond left, single down, double bond right, single down, single left. I could also swap top and bottom. And so I'd have a structure that had a sulfur, double down, double right, single up, single left. I could also swap my bottom and my left here. And so I'd have one that is a sulfur, double right, double left, single up, single down. Keep doing this. Basically, you'll notice that we're having opposite sides for my doubles, or I have right angles. I could also have drawings where I have the other right angles. So a sulfur, double left, double up. And the last one would be double left, double down. Basically, all the possible combinations of organizing those 4 things around the sulfur. The reality is that there are 6 equivalent valence electron configurations, 6 equivalent resonance structures for SF4. The reality is it is a hybrid of them all. It is not one or the other. We simply can't draw the real structure. In general, what this will mean is if you're asked to show the resonance structures, you'll have to show the possibilities. But if you are just asked to show, say, SO3 2-, which has multiple possible resonance structures, unless you're asked for the resonance structures, you just draw one. And so if you just said, hey, draw this ion, you'd put your atoms down. You'd put your extra electrons on. You'd bond. And then you'd have to break up a lone pair. One more from each of those. And you end up with a sulfur, double bonded to 1 oxygen, single bonded to 2 oxygens with a lone pair on it. And often we do put the other atoms' lone pairs. It is a central atoms lone pair that we are very concerned about and definitely need to keep on. Often you'll notice that Lewis structures start leaving off lone pairs for the outside edge atoms because they don't affect the shapes. But it's good at first to include them so that we can make sure we're tracking and getting our octets where they should be. And so this would be the Lewis structure for sulfite. This is not the resonance structure. That would be a series of 3. But this is the Lewis structure for it. Just depends what we're asked for. Most of the time, you will be asked for a Lewis structure, not the resonance, unless it is specifically asking you for resonance issues. How do we know that it's definitely the hybrid? Well, we can actually measure bond lengths and charges. But one of the most common is that you don't have to have ions to have resonance. If you've got 6 carbons in a ring with a hydrogen off each, so speed Lewis structure here, this is benzene. It is often written like this just for clarity, just cuts down a number of things. It's got 3 double bonds. But if you draw the Lewis structure outright, where you put the dots on and connect them, you could have also connected it this direction. They're equivalent. You could have chose left or right. And so this raises a question, well, which is it? It's a hybrid of the 2. It isn't actually one or the other. Effectively, this lone pair can fold down to attack that carbon, which breaks this one off to attack that carbon, which breaks this one off to go attack the carbon that we lost stuff at the beginning. In doing so, you create that image. Benzene has a resonance structure. No charge is necessary. You don't have to be an ion to have resonance structures. It's just very common for them. Well, when we first were studying the idea of resonance, one thought was that no, they really were going between them, that it was the first on the left and then it was on the right and then it was on the left, that they were changing. Problem is, they were doing it so quick we were seeing bonds that all looked 1.5 bond instead of a single and a double. Well, if you ever move your hand in front of a camera, like at night, you'll notice it blurs. Basically, if you're watching with a camera and something is moving, you kind of see the blur of its motion. And so the idea was we were shooting X-rays at these and we were testing, and if our atoms had been at one size and we were watching for a while and they changed back and forth while we watched, we would see the average. We'd see it somewhere in the middle here. Well, the way you fix on a camera is to take the photo faster. If you don't give it as much time to move, it won't move as much and you won't be seeing as much blur. And so we made faster devices and we tested quicker and quicker and quicker, and basically it always looked like 1.5. And so the final idea was you had two options. It either was 1.5 bonds, or it was moving so fast that even with our best equipment, it still was blurring out. Well, you can do some math. Basically, atoms are on a spring. And so if I have my spring expanding and contracting, I have some weights on it and I know how fast it's going back and forth, which we could say what was the minimum speed it had to be going to still blur in our efforts to see it. We could figure out the speed. And even though it's atoms moving over angstroms, that would still have to be so fast that the energy contained in the bond would rip the bonds apart. When they did the math, they said there's no possible way it's moving this fast. Even that light a particle moving that small a distance would have to be going so fast it would have destroyed the molecule. And so the final conclusion was that it couldn't be doing that. It had to actually be 1.5 bonds the entire time. And so benzene is often drawn as just a circle now, because the reality is those double bonds are spread out. They're not between any specific atoms. They are spread over the whole collection. So resonance is really about the fact that Lewis structures can't represent the reality. They can't represent these hybrid shapes. As we get further into orbitals, molecular orbitals we'll start to see how this plays out in reality for constructing the molecules. This is how we do it with our Lewis structures for drawing.